Start recording. Where is the, there it is. Back, down. Share screen. What happened? Oh. Okay, there we go. All right, now. Okay. So today we're starting a brand new topic. Which is integration by parts. AKA use substitution on performance enhancing substances. Okay, so I'm not going to necessarily say it's steroids and say that it's illegal because it turns out you're allowed to do it in calculus, but it's definitely performance enhancing substances. All right, so we need the setting of what would be an example of the kind of integral that we might see of where we would be curious about using a brand new technique. In other words, what's an example of something of where we can't do it using just what we currently know? Okay, it turns out we don't actually have to search very far for an example of something that we can't answer. And this is a not that crazy function. I mean, the natural log is something that we use all the time, and we never came up with an antiderivative for it before. So that's a bit of a problem. And it turns out that because the natural log is used so heavily in science, that we want to be able to find the antiderivative of it. So this is actually something that's quite necessary. And so we need to figure out a way of answering this question. Okay, so what we're going to do then is we're going to see what our theorem is. So theorem Now, those are two different letters. It's U and V. And they're two different letters on purpose. V du. Okay, now, when we do U substitution, we're substituting for a single thing. When we're going to do integration by parts, we're going to substitute for two different things, for two different types of letters. So that's why I refer to it as U substitution on performance enhancing substances, because we've just kicked it up a level. We've just made it twice as effective. There's a whole lot more that we're going to be able to solve using integration by parts. And the theorem is the integration by parts theorem. Now, I think, and don't quote me on this, but I think it does have a fancy name. So everybody just calls it integration by parts. But if I remember correctly, this is also called the D'Alembert theorem. So it's a French name. So don't expect me to quote it correctly in terms of pronunciation. But we're not going to use the fancy name for it. We're just going to call it integration by parts. Okay, well, let's investigate where is this coming from. So let's review a little bit for ourselves. Suppose that we wanted to take the derivative of U times V. I think we would know how to take the derivative of that. That would just be, the product rule. So it would be the derivative of U times V plus the derivative of V times U. Sounds about right. Okay, well, that means then that if I take the antiderivative of the derivative of U times V, I know what that has to equal. That's just U times V, because that's the fundamental theorem of calculus, right? So this is fundamental theorem of calculus right there. That's what makes that happen. Okay, well, not only that, but then because we know what that's actually equal to because of this, we could rewrite that. So we could say that this is the same thing as the antiderivative of the derivative of U times V plus the derivative of V times U. Great, that works. Well, now then what we could do is that we could say, let's rewrite this ever so slightly. And that's really equal to a U times V, by the way, because that's still the far left side. Okay, so could someone tell me what I just did there? I just changed the order, right? That doesn't actually change anything, does it? Because those are multiplied. Okay, so I just flipped them because that way then it looks like the usual order that we do things. So I could rewrite it like this, correct? That's not a big deal. Okay, what did I do on this line? Yeah, I subtracted that part and moved it over to the other side. Okay, but this now, this was what we had up here. Okay, so that means that we just reached where the theorem comes from. Where does the theorem actually come from? Well, what was the first step that we did? Blank rule. Product rule. And then what did we do to the product rule? We, well, right here, used what? The fundamental theorem. So if we use the fundamental theorem on the product rule, we get this rule. So it's not so far off from stuff we've done, right? It's really just combining two things that we've done before. But as a result, it gets a funny looking rule, because it is a funny looking rule. Okay, so let's now learn how do we apply this rule. And there's actually like a handy mnemonic. Anybody know what a mnemonic is? It's a fun word. So I got one nod yes. So what's a mnemonic? Yeah, it's a saying to help you remember something. Very well stated. Thank you. So there happens to be a handy mnemonic for knowing how to use this theorem. So we're going to learn that. Then I'm going to show you an example. Okay. So we're going to learn how to use it, and then we're going to use it. Now, I did not invent this. This is like a very old mnemonic. There's nothing wrong with it, so I didn't need to preface it by that. But it's Lipit. Okay, now, Lipit stands for something. So this is for make the choice of you according to Lipit. And what does Lipit mean? Logarithm inverse function polynomial exponential no metric, I think I spelled that right, trigonometric, and that's Lipit. Okay, so Lipit is really not just is really an acronym. I think an acronym is one of the ones where you can actually pronounce the word, but I don't know that that's a real word. So maybe it's not an acronym, but so Lipit, L-I-P-E-T. Okay, so let's see our very first example of using this, and we're going to answer the example that we started with, which was trying to find the antiderivative of the ln. So I'll wait to make sure that everybody catches up with writing. That way I don't leave anybody behind. "60 degrees on Saturday." It's going to be pretty fun. I don't want to jinx anything, but it's supposed to be 81 on Wednesday when we get our break day. So Oh, I forgot to ask, was everybody done writing? Okay. Okay, so we have to identify two different things now. So let's rewrite the theorem. It says that we have this, and it's going to be equal to this minus that. Okay, now, when we have our theorem, there are two different things then that we have to identify. We have to identify a u, and we have to identify a dv. And I'm going to be explaining that by doing this example. The u is what we choose. The dv is all the rest. Okay? So the u is what you choose, and the dv is all the rest. So that's the way of kind of understanding how we're going to do what we're about to do. So the u has a special method for selecting it. It's the lipid, and you go in order. So the very first thing that you look for is you look for if there are any logarithms. Are there any logarithms in this problem? Yes. So that's our u. So I don't look for any inverse functions. I don't look for any polynomials. I don't look for any exponentials, and I don't look for any trig functions because I had the logarithm. Does that kind of make sense so far? I mean, this is the very first example, but does it make sense that that's the reason why we're picking the u? So it's a methodology. Now, dv is everything else that appears in the problem. Now, that means that I have to write down everything that's not the integral symbol. Well, what's the only thing that's not the integral symbol in this problem? Dx. That's the only thing that's not the integral symbol. Okay, now our next step is that we need to then look at, and what will this theorem require us to also write down? It will require us to write down a u. Well, we already wrote down the u, so we're good there. It will require us to write down a v. Ooh, we don't have a v written down yet. But we're going to come up with a way to find our v. So we'll be good in just a moment on that. We'll need to write down our v. Okay, well, so if we've already found it, then we can just plug it in there. And we'll have to find our du. Well, that means we're going to need to take a derivative of our u. So let's do that first, and then we'll find our v. Du dx is equal to 1 over x. Okay, that's pretty good. And then that means that du is equal to 1 over x dx. Now, let's stop, okay? And let's talk about this. When we do u substitution, we're doing steps very similar to this, right? But for u substitution, we would go one step further on this. What would we do for u substitution? We then solve for what the dx is. Do we need that here? No, we don't. So it's like we're stopping short on what we would do for u substitution. But really what we're doing is we're stopping there and then continuing our energy somewhere else. That's the best way to think of it. So it's really not actually any longer what we're doing here. It's just that we then suddenly divert our energy because we don't need to go further. But by setting up our u substitution the way that we did, we allow ourselves to make it a similar process. But it's important to know I do not solve for my dx here. I don't have to. So all I need is my du. Okay, so I now have my du. Now I'm going to come up with, how do I find my v? Well, v is the antiderivative of the derivative of v. Does that sound about right? I hope so, because it's true. And what lets me say that, by the way? What would allow me to say that v is equal to the antiderivative of the derivative of v? There's some sort of theorem. They do cancel each other out. That sounds fun. And yet, it also seems kind of mental. What would be the only thing that we could possibly have that's both fun and mental involving calculus? The fundamental theorem of calculus. That sounds like a really good choice. So now we agreed that the derivative of v was going to be equal to the derivative of x, right? Because we said dv equals dx. So that means that this is also that, right? Well, so we're going to then say, well, that's then really an x. Now, we could write a plus c here. We could, but we're not going to. Now, what's the reason why? Because at the very end of the problem, when we're all done with all of this stuff, then we'll write our plus c. We're going to save that for the end. Okay, so it will come in and it will all work out and we'll get the plus c's and then all of math will celebrate because we've done the right stuff. But we're going to hold that off for now. So we now have everything that we need because we have what u is, we have what v is, and we have what du is. And that's all of the parts that we need. Okay, so now let's then solve our question. Based upon how we substituted, this is u dv. And then by integration by parts, this is equal to that. So now I'm going to multiply the u and the v together for what I found them to be. ln of x and x, and then I'm going to write an integral symbol, and I found my v to be x, and I know what my dx is. Okay, so I'd like to pause for a second to make sure everybody then soaks it in to catch up to where we're at. So the terms that I just wrote down, can you match them up with where they're coming from? Anything seem like a mystery? This is a good time to ask if things seem like mysteries. Yes?
How did you get x for v?
So I got x for v from right here. Okay, there we go. So right here, I said that dv equals dx. So then v is the antiderivative of dv. Does that part make sense? Okay, well then, if I keep the integral symbol, I can replace the dv part, which is right here. But this, the antiderivative of the derivative of x, is x. So if I underderivative x, I get that. But on the left, we had this. And then on the far right, we have this, which means that v equals x. Does that help? Other questions? What could you ask before we go further? We're not done. We're just almost done. Good for the next step? Okay. So will you allow me to write that first part like this? Is that okay? So that was just, I changed the order of the multiplication, right? Okay, well now I'd like to write what I'm actually integrating now. Are there any suggestions for how to simplify what I'm integrating? Cancel the x's. I agree with that. That seems like the thing to do. So they'll cancel down to what? They'll cancel down to 1. Okay, so what is the antiderivative of 1? It's x. Well, now I'm going to put the plus c in because that was then a final antiderivative I was finding. So here's where it's fair to put the plus c. Well, so that means that what we just found was that the antiderivative of the ln of x is equal to x ln of x minus x plus c. Not bad. That's pretty cool. Okay, because we just found a brand new antiderivative, let's check it. Let's check that this works by taking a derivative. Okay? So if I take the derivative right here, I know what I should get. What should I get? I should get the ln of x, because we just said that all of this stuff that's in the parentheses that I just wrote is the antiderivative of the ln. So if I take the derivative, I should get back to the ln. Well, let's see if it works. Okay, so I'll have the first times the derivative of the second for this part that's the product, right? So I have to use the product rule right here. So first times derivative of the second plus the second times the derivative of the first minus, well, now I have to have the derivative of x, which is 1, plus the derivative of c, which is 0. Then we go, darn it, I wanted that to be the ln. And that looks nothing like the ln, does it? Well, I should probably simplify. That seems like the thing to do. Still doesn't look like the LN. I should probably actually simplify. Okay, that was the LN. It turns out it works. Not bad. That's a pretty cool rule. That was kind of fun, I gotta say. Or at least I think so. Are we ready for another example? Let's do another example. Okay, so inverse tangent. I don't think we've ever found the antiderivative of this before. I'm fairly certain we haven't, because I don't think we could have. Okay, so let's see if we can figure out how to do it. Now, I didn't bother telling you this for the last question because it very clearly was going to be an integration by parts, because it was the very first example I did after giving you the integration by parts theorem. So now I have to tell you, how do you know to use integration by parts? Okay, there's an ordering for how you select things. When you have an integral, the very first question you ask is, does it match with one of our basic formulas? Okay, what's one of our basic formulas? Antiderivative of the sine, antiderivative of the cosine, power rule. Like that's pretty much it, right? Or maybe it's like the antiderivative of the secant squared, something that we just have memorized. Or antiderivative of e to the x, or antiderivative of 1 over x. That's like that. Those are our basic formulas, right? Those are the ones that we've been doing a lot of. Okay, so that's check number one. Is it one of those? Well, we'll do that for this. Is it one of those? No, it's not. Okay. Next level. Can you do a U substitution? Well, okay, well, we look at this and we think, well, what would we even try to make U? The only thing that we could possibly do is to either make U be equal to X, and that's just relabeling the variables, which doesn't help, or you make U equal to all of the inverse tangent, which doesn't help because then you have to know what the antiderivative of the inverse tangent is, which is what we're trying to find. Okay, so doesn't help. Doesn't help at all. So the next level past U substitution is U substitution on performance enhancing substances. So that's the reason why we're going to try integration by parts. It's because nothing else worked. So now it makes sense to try it. So now let's use then our methodology. Let's lip it. Okay, so we want to pick our U. U equals. We also know that we're going to have a dV. So in picking our U, we're going to go through. Lip it. L. Logarithm. Do we have a logarithm in this problem? We do not. I. Inverse function. Do we have an inverse function? Ooh, we do. Do I bother checking past there? Nope. I stop when I reach the one that works. So U is equal to the inverse tangent of X. And now I need to know what the dV is. Okay, well, the dV is all the rest of the stuff in the problem. Well, what's all the rest of the stuff in this problem? Dx. Okay. And a bunch of fun random lines thrown in for free. Okay. Dx. There we go. Okay, well, let's reverse order this. V is the antiderivative of dV. So that has to be the same thing as the antiderivative of dx. which means that v is equal to x. Well, that's very similar to the last problem. That was the same dv part. So now then we're going to try to find what our du is, because we know that we're going to end up using that. So du dx is equal to, okay, so we have to remember what the derivative of the inverse tangent is. So do we remember that? One over 1 plus x squared. I agree. That's one of those strange ones that we don't have to use too often. Which means that du is equal to 1 over 1 plus x squared dx. Okay, now, just a comment. Let's suppose that we were taking an exam and we realized that we needed to know what the derivative of the inverse tangent was. And we're sweating it out, and 5 minutes passes, and then we're like, oh, no. Like, I can't remember what the derivative of the inverse tangent is. Okay, well, there's something you could probably try in that moment that very few people, at least in this course and this semester, will try, which is that you could try asking me. It doesn't mean that I'm going to tell you, but I mean, there's very few times I think I've ever told anybody in this course no on anything. So give it a shot. You know, I might give you a hint that's helpful. Like I might say something like, oh, why don't you try 1 divided by 1 plus x squared? Which would be a really good hint. That would probably put you on the right track. Because I'll tell you that that's not really the main point of the problem. That's kind of like you just need to know that to be able to actually do the real part of the problem. So would I deny you that? I don't know. I mean, I could, but it doesn't sound likely. So in the off chance that you were sitting down for the exam and then didn't have a clue how to do a part like that, you're very welcome to ask me and see what happens. Again, no promises, but just know that that's an option at least. Okay, so now we have all the parts because we have our u, we have our du, we have our dv, and we have our v. So let's now solve. So this is really equal to u dv, which by integration by parts is equal to u v minus v du. And now let's put all those parts together. So u times v is equal to tangent inverse of x times x minus, and then I need an integral symbol, and x times 1 over 1 plus x squared dx. Okay, so now let's do a little bit of rewriting. So anybody mind that I changed the order? Is that okay? And now I have this integral that's there, which kind of means I probably need to solve that integral. So I need a way of solving that integral. Okay, so the first thing that I try is it one of my basic integral formulas? So is that like a power rule, or is that like an e to the x or a 1 over x, or is it anything like that? Nah, it's not. Okay, so once that doesn't work, what's the next thing that I try? I try u substitution. So what would be something that I could maybe try as a u substitution for this? What should I make u be equal to? That sounds like a really good choice. So just to be clear, we're doing a u substitution in the middle of an integration by parts problem. So du is equal to dx, or pardon me, du over dx is equal to 2x, which means that du is equal to 2x dx, which means that dx is equal to 1 over 2x du. So as you can see, that's a similar process to what we do in integration by parts. It's just that we carry it a step further. So continuing this problem, it's x times the inverse tangent of x minus x times 1 over, well, that's a u there. And then this is a 1 over 2x du. Well, now I get to do one of my all-time favorite things in math, which is I get to cancel things. Before I go to the next step, let's make sure everybody's kept caught up. So now the next thing that I want to write is x inverse tangent of x minus 1/2 antiderivative of 1 over u du. Well, what is the antiderivative of 1 over u? The natural log of u. And then I just switch back with what my u was. Now, which u do I use? Do I use u that's the inverse tangent? No, not that u. Why is it not that u? Yeah, I have to finish the step that I'm actually in. The step that I'm in is u substitution. Now, here's the thing. I could invent an entirely different vowel if I wanted, and have that be what I substitute for the substitution. So for instance, since I already used the U, let's see, our vowels are A, E, I, O, U, and sometimes Y. So I could invent I could invent Y substitution. Ooh. And so I could then say Y instead of U here. And so if I wanted to make sure that everybody was clear that it was something different, I could label it different. Or because I'm an incredibly patterned person and just don't feel like I have to change, I could just still have it be a U, and then just make sure that everybody knows that I need to use the right U, the U that's in the U substitution that I'm doing. And there we go. And that's perfect. Okay, so let's do the following as our last example. U equals dv equals. Okay, so first question we have to ask is this one of our basic integrals? Answer, no. Is this something that we could use a u substitution for? Well, we'll just think through in our heads. If we make our u be equal to the x, no, that's not going to work. That's just relabeling it. If we make our u be equal to the ln, well, then our du is 1 over x, which doesn't appear in the rest of the problem. So that doesn't seem like probably a good choice either. So it's probably going to be an integration by parts. So we now go through our limit. Log, ooh. Okay, so we don't have to go any further. Now, what's all the rest? X dx. So that's different. Which means that if I want v, I'm going to have to find the antiderivative of that. Can I do that? I think so. One half x squared. Now what then is my du? Well, that's 1 over x dx. ln of x dx is equal to u dv, which is uv minus v du. Now, there is also a mnemonic for remembering what this right-hand side is. So some people would refer to this as UV as ultraviolet, and then V du as voodoo. So sometimes to remember it, you would say ultraviolet voodoo, which is kind of a fun thing to say. So that's the right-hand side, ultraviolet voodoo. Which sounds like something that would give people superpowers in some sort of comic book. Okay, so now let's take then the U times the V du. Okay, so let's rewrite that into the front. And let's get rid of those bunch of random lines that just got put in. Let's pull that constant into the front. And let's simplify the x squared times the 1 over x as just x. And we're done. Okay, so what I'm gonna suggest is that tomorrow, let's do a WebAssign day of where we'll work on these problems so that we immediately get practice on these. Now, this is another topic of where if you work at it and get good at it, it becomes easy. Because then you'll never have to guess what to do. Now, there may be one problem on the WebAssign we'll purposefully hold off on doing until I lecture one more time, okay? So if we reach that problem, then I might say, let's hold off on this until I lecture on it. Have a good one.